Hey everybody, so let's continue on with our math discussion. Today we're going to learn about the cross product. Now the cross product you often learn alongside with dot products in your vectors, and it's defined as the following. If I cross product a vector p with a vector q, then you'll get the length of p times the length of q times the sine of the angle between them, that's an alpha, times some vector n. So let me just quickly describe what this n is. This n is a unit vector. Remember, a unit vector is length 1, right? So it's a unit vector orthogonal to both P and Q. So if I draw this out, I can draw two vectors. I'm going to draw P up here. This is my vector P. I'll draw Q down here, Q. Now this alpha here is the angle between them, just like with the dot product. We can get the length, we can get P, we can get the length of Q, but how on earth can I make a vector orthogonal to both P and Q? It's impossible, right? If I make one orthogonal to P, it's no longer orthogonal to Q. So what this requires is another dimension. So how is this possible? So it requires this third dimension. So it goes out into the z-axis. So x, y, out of the screen or into the screen. So it goes along that axis. So we get a vector along the other axis in the z direction, either positive or negative. And that's our unit vector. So what we get is then a new vector. So P and Q, the size of P is a scalar, the size of Q is a scalar, sine's a scalar, and we get this unit vector n. So we get a vector orthogonal to both P and Q, either positive or negative, and the length of it is defined by this size of P times size of Q times sine. So far this might seem a little random. So let's start to unwrap this. First, because it goes into the z direction, this is important to note. The cross product is only defined in 3D. There's no other version. It's a 3D operation, but we'll come back to what we can do with this in 2D. It's kind of fun. Yeah. Okay. So then, given P and Q on a plane, right? Of course, any two vectors form a plane. That's just, no matter where you put them, they form a plane. Then the cross product results in a vector pointing straight off from the plane. So either pointing in or out of the plane. In this case, our screen, right? So if I have two vectors on my 2D screen, I do the cross product, it comes out of the screen or the other way. That's the only way to get this orthogonal, to have something both orthogonal to A and to B. So let's start unpacking this. So we've talked about the n. It's a unit vector orthogonal to one or the other. Excuse me. Let's point out. Let's unpack this sine wave here. And we did this for cos, so this should be no surprise here. Here's my sine wave. 1 and minus 1. So the first thing I want to highlight is that, where am I? We should keep our, yeah. So this sine here, when it's 0, right there, or right there, then this happens when they are codirectional vectors, right? Right there and right there, we get a 0. If we have a 0, then this whole thing collapses. and the whole thing becomes 0. So if we have co-directional vectors, if the vectors are pointing in the same direction, we ended up with a 0. We also get that in this case right here if they're pointing in the opposite direction. Right? So if you have collinear co-directional vectors, or one's the opposite direction, so if I have a vector like this and the other one like this, or if I have one like this and one like this, then we're going to get a 0. Okay? So that's our first thing. If P, Q are co-directional or opposite, this results so result is a 0 vector. Okay, so if you cross product two co-directional or opposite vectors, you'll get a 0. You're not going to get a vector out of it. Okay. Now the other points of interest on this graph here are at the peaks, +1 and -1, and I want to highlight this because it helps us understand some really cool property of cross products. So if P and Q are orthogonal, if P, Q are orthogonal, right? So either they're 90 degrees or -90 degrees, we're going to get sine to be 1. If I look at our thing up here, sine will be 1, so the result is just the length of P times the length of Q in this new direction, okay? So if they're orthogonal, it's just the product of vector lengths. Now this might not seem that interesting to you, but let me draw it out and you'll see, hopefully quickly, why this is interesting. So here's another thing. Now just bear with me. I'm going to put them straight like this. So this is a straight up and down vector. This is a straight left and right vector. This is Q. This is P. Okay? Cool. So they're orthogonal. Good. And if they're orthogonal, then my cross product gives me the product of their lengths. The length of P times the length of Q is the area of the square, right? So if P and Q are orthogonal, it just gives us the product of vector lengths, which actually is the area of the square. Times the Q area of square. Awesome. What's really cool about this is because of that sign, and I'm not going to get into too much of the math, you're welcome to look it up, but because of that sign, it turns out this property holds for all parallelograms. So let me show you what I mean by that. So I'm going to write this out. It turns out that this property, where the cross product will give us the area, this turns out that this property holds for all vectors with the cross product. Let me show you what I mean by that. Okay, so I'm going to draw a couple more vectors out here. So if I draw this one here, if I draw that one there. Now that sign is so awesome because it takes the proportion of that square, and as you shrink it in, that proportion shrinks as your sign changes as well. So here I'm going to draw this out. If I take the cross product of these two vectors I've just shown you, A and B, it'll give me the area of this parallelogram made by those two vectors. So P cross product Q actually gives an orthogonal vector that we've talked about with length matching the area of the parallelogram. Oh my god, how do I spell that? I hope that's close enough to understand. Matching the area of the parallelogram defined by P and Q. Okay, so it'll give me the area of this parallelogram. Awesome. Now, often in graphics, as we'll learn very shortly actually, we deal with triangles. So the cool thing about this is, to get the area of my triangles made by these vectors, I just divide it by 2. Cool, that's it. So then this is something you might find yourself doing a lot of. If I take P, I cross product it with Q, it'll give me a new vector orthogonal to both. The length of that vector, it matches the area of that parallelogram. So I take the length of it, cool, and then I just divide that by 2. This is the area of the triangle. I'm going to write this out. Cool. So if you find yourself needing the area of the triangle, you can just do the cross product on the 2 vectors of any 2 sides of the triangle, and you'll get the area of that triangle. That's really awesome. It's so awesome, I'm going to highlight it. What else do I need to highlight? This part here. Whoops. Let's not erase it. There we go. Okay. Awesome. So our cross product is great. It gives us an orthogonal vector. Right now, you might not see why it's useful to have an orthogonal vector, but trust me, it'll come up very soon. Any 2 vectors, I can cross product, I get an orthogonal vector. 2, it also tells me the area of that triangle, okay, which is really super useful. So that's cool. So we know we can use a cross product to get the area of a triangle. We can use it to get the orthogonal vector. But we have a similar problem that we had. We have a similar problem that we had with the dot product. It's expensive to calculate. Okay, so we have this problem. It's expensive to calculate. If I go back up, we have 2 sizes, so that's 2 square roots, and a sign calculation. Those are expensive, and if you need to do a lot of it, it's slow. Luckily, we do again have some shorthand from linear algebra. Now, I'm not going to show you how that's derived. You're welcome to look it up, but we have the shorthand from linear algebra. Where we can just calculate it with multiplications and additions, okay, or subtractions. So the way we do this, you should have learned this in your linear algebra course, but I'll quickly review it here. If I want to get P dot product Q, which we've already learned is the length of P times the length of Q times the sine of the angle between them times that normal vector, we can actually just do it using this shorthand, x, y, z. And if I have px, py, pz. Hold on a second. Yeah, that's wrong. Let's try that again. Aha. Px, qx, py, qy. I don't know why I'm struggling with this one. Pz, qz. There we go. Okay. So the way that you do the cross product, again, look it up in your book, look it up online, but I'll quickly go over it, is I calculate the x, the y, and the z of the new vector independently. And the way I learned it was, for x, I cross out the top, I cross out the x, and then I multiply and subtract. So I have py times qz minus pz times qy. This is my x, okay? Awesome. Can I erase that without killing everything? Great. That's the x. For the y, I do the same thing. I cross at the top, I cross out the y, and I do the cross again. So for the y, it's px times qz minus pz times qx. Awesome. Right? Py times this times that. And let's see if I can clean this up a bit. That's not so bad. I can fix that. Okay, and then for the z, we do the same thing. We cross that out, and then we go crossways like this. It's px times qy minus That's right, it is a p. I knew I wrote that wrong. There we go. Minus py times qx. Awesome. This is my y coordinate, this is my z. Let me just double check my notes. pxqz minus pzqx. Cool. pyqy. Aha. Py times qx. There we go. Don't trust me anyway. Look it up. This is just meant to be a quick refresher for you. So then the answer to my math here is the following. So p, the vector p cross product the vector q is going to be the big following thing. The x coordinate is py qz minus pz qy. This is my x. Then the y coordinate is going to be px qz minus pz qx. It's an x, and the y coordinate, z coordinate will be px qy minus py qx, like that. And I'll annotate x, y, z. So you can do that calculation. This will give you that vector that's normal, without doing those square roots, without doing those expensive square roots and sine waves. So it's a lot faster. This will result in a right-handed orthogonal vector. You should know right-handed and left-handed systems already from like physics or from high school math, but just in case you don't, right hand, left hand. Awesome. I hope it comes through right. Yeah, it does look right in there. Okay. Right hand vector. If I have A, I have B. I match them up. Z will be my next finger. Okay, mine doesn't go the other way. Yours might, mine doesn't. That's the right hand rule. A goes this way, B goes that way, then it'll give you a right handed, it'll face this way. So previously when I said, hey, look, we have N going in or out of the plane, now you know which way it's going to go, depending on P and V, okay? All right. So I want to talk a little bit about what's called a 2D cross product. Now, as I said, cross product is only done in 3D, okay? So we can't really do this, but it's going to come up in graphics. A 2D cross product, we just get the magnitude of the imaginary orthogonal vector. So I say imaginary because if I'm in 2D, I don't have a z dimension. It's imaginary, right? So let's draw this out. I have x, y, z, right? px, qx, py, qy. I don't have pz. That's okay because I get the length of z. I do this. I do my cross product. Cool. So it's going to be, if I take the p, q, and I'll take the size of that, basically, of that vector. I'll make a note here. This is 2D version, right? Come on. This is not going well. In 2D, there we go. This is just going to be px qy minus py qx. That's it. I'll also make a note here if you're a math nerd. That should be an x. Okay. This also happens to be the determinant of the 2D matrix that we just made there. But that's not relevant at this point, of course. But it's kind of cool. So that's it. And this is really useful. This gives us some information. Okay, it gives the area of the triangle, which is great. You need to divide by 2, of course, remember that, because it gives you the parallelogram, actually, not the triangle. It also gives you the sign, so whether it's positive or minus. And this tells you whether it goes in, positive comes out of the plane, negative goes into the plane. It actually tells you if the vectors are clockwise or counterclockwise with each other. Clockwise, counterclockwise. of course, in a right-handed system. And this might seem kind of useless or random, but I'm giving you a toolkit because in the next classes, we're going to be using these toolkits to solve problems, and hopefully you'll see how cool and useful this is. So here's my vectors P and Q. The cross product of P cross product Q is going to be, the magnitude of that is going to be less than 0 because it's clockwise, right-handed rule, and it's going to go into the plane if you twist your arm that way, right, for clockwise. And then the size of QP, right, same vectors, but now I'm going the other direction. It's going to be bigger than 0. It's going to be counterclockwise. Remember, there will be 0 when they're collinear or in the other direction, which is a problem. All right, so that's cross products. Cross products are awesome. You're going to use them to find orthogonal vectors, and you can do it without heavy math. It's just a few multiplications. I'd recommend, if you're really rusty on this, review my notes, but maybe look it up online or check out your linear algebra textbook. So we'll stop there for now. Thanks.